So we should be recording now. So tonight we're going to try to connect what we've been studying with functions and the characteristics of one-to-one and on-to with sets. And the sets we talked a bit about before exam 2, but now we're going to kind of look at a topic that combines the study of the two. So I'm going to share. Believe this is what I want to share. And so what we're going to do is we're going to connect these ideas by considering sizes of an infinity. So to get started, so hopefully we'll have some fun tonight. We'll have a little bit of discussion. We'll watch a couple videos related to this topic. Hopefully you enjoy this conversation. So to start with, we first need to recall or remember a few things from our study of functions. We need to remember what one-to-one functions are. We'll need to remember and use what it means for a function to be on-to. And then we'll need to recall what it means for there to be a one-to-one correspondence between the domain of a function and the codomain of that function. Okay, so as a quick reminder, one-to-one functions. So a function is said to be one-to-one, or sometimes we use the 1:1, or we say injective. In higher level mathematics, we tend to use the word injective. So a function is injective if and only if no two elements of the domain match with the same element of the codomain. So in this diagram here, we have a possible function. On the left, we have a domain X with 4 elements, and we have a codomain Y, and we can see that each of the elements in X is matched with an element of Y. And as we look at the elements of Y, we notice that no elements of Y are matched with more than one element in X. So we say, mathematically, we say F maps X to Y is one-to-one if and only if for all X1 and X2 in our domain, if F of X1 equals F of X2, then X1 has to be equal to X2. So for a function to be one-to-one, the outputs of the function, if they are equal, then the inputs have to be equal. Okay, so that was one-to-one. Now let's remind ourselves about on-to. So a function is said to be on-to or surjective if and only if there is no element of the codomain that is not matched. So let's go back and take a quick look at our previous slide. Notice that this function is not on-to. There is an element in set Y that is not matched with an element in set X. So f of X, or F mapping X to Y, is on-to if and only if for all Y in my codomain Y, there exists an X in our domain such that F of X equals Y. And then our one-to-one correspondence or bijection, and not every function is a bijection, but to be a bijection or to have a one-to-one correspondence, we saw that a function has to be both one-to-one and on-to. So an example right there of what that looks like. So no two elements of the domain match with the same element of the codomain. And then there is no element of the codomain that is matched with an element of the domain. So the function is both 1-to-1 and on-to. So now let's talk a little bit about set size and the idea of a 1-to-1 correspondence. So there are 118 chairs in a given university lecture hall. An unknown number of students enter the room. If every seat has exactly one student sitting in it, and there are no students not sitting in a seat, how many students are there in the room? So I want you to take a second, think about that. Do not put your answer in the chat yet. Okay, so there's 118 chairs. Every seat has exactly one student sitting in it, and there are no students not sitting. How many students are in the room? Go ahead and drop your answer in the chat. Okay, I'm seeing 118. I see a less than or equal to 118. I see an at least 118. Less or equal. Okay, good. So let's talk about it. Thank you for sharing your thinking. So if there's 118 chairs and we don't know how many student, oh, it's not marking up. Hold on just a second. Annotate, draw. Okay, so we know there's 118 chairs. We don't, right? Initially, we don't know how many students are in the room, but we do know that every student has exactly one, or I'm sorry, every seat or every chair has exactly one student sitting in it. So every one of those chairs is occupied, and there are no students that aren't sitting. So there's no students on the floor. There's no students standing. There are no students not in a seat. So if there's a student in the room, the student is sitting in a seat. So how many students are there? There's 118 students. Does that make sense? All right. So then, in this particular case, oh, come on. All right, let's do it this way. We have two sets, a set X, that would be the set of our chairs, and a set Y, that would be the set of students. And they have the same size if and only if there exists a function X mapping to Y that is a 1-to-1 correspondence. Okay, so are there any chairs? Are there two students in a single chair? No. Is every chair occupied? Yes. So it is both, in this particular case, students sitting in chairs in this lecture hall is a 1-to-1 correspondence because it is both 1-to-1 and on-to. So, oh, I need to erase that. Clear. So let's make a distinction now between the idea of a finite set and an infinite set. So a finite set has some size. We can say the size of that set could be size n. And it can be put into a 1-to-1 correspondence with the set of the natural numbers, 1 through n. So a simple example. Here I have a set A. And in my set, I have 4 shapes. I have a star, I have a heart, I have a smiley face, and I have a lightning bolt. Okay. The size of this set is dictated by how we can put this in a one-to-one correspondence with the set of counting numbers. Now, this is a rather small set. We can look at it and we can say, well, the size of that set is 4 because I can see that there are 4 objects in there. So I would agree, yes, the size of that set is 4. But what we want to do is focus on this idea that it can be put in a one-to-one correspondence with the set of integers. And by the way, this PowerPoint is up in Canvas. So if you want to just sit back and pay attention and not necessarily take notes, that's perfectly fine because you can download it. So what this means that we put it into a one-to-one correspondence is we take each one of our shapes and we map it to those counting numbers starting with 1. So for example, we can take the star and map it to 1. We could say star is the first element of the set. The heart is the second element of the set. The smiley face is the third element of the set. The lightning bolt is the 4th element to set. We have no more objects in our set, so we stop counting there. And so this 4 here, it becomes the size of our set. Now, an infinite set is a non-empty set that cannot be put in a one-to-one correspondence with any finite set. Okay, so an infinite set would be something like a set we have here, A, but the number of objects or numbers or whatever you want to have in that set is such that I cannot pair it with a counting number like I could with the star, the heart, the smiley face, and the lightning bolt. So what we're going to do is we're going to see a short video that kind of introduces this idea of an infinite set. Now, I would like for someone to give me a thumbs up indicating that you can hear that. Can you hear?
In the 1920s, the German mathematician David Hilbert devised a famous thought experiment to show us just how hard it is to wrap our minds around the concept of infinity. Imagine a hotel with an infinite number of rooms and a very hardworking night manager. One night, the infinite hotel is completely full, totally booked up with an infinite number of guests. A man walks into the hotel and asks for a room. Rather than turn him down, the night manager decides to make room for him. How? Easy. He asks the guest in room number 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Every guest moves from room number n to room number n plus 1. Since there are an infinite number of rooms, there is a new room for each existing guest. This leaves room 1 open for the new customer. The process can be repeated for any finite number of new guests. If, say, a tour bus unloads 40 new people looking for rooms, then every existing guest just moves from room number n to room number n plus 40, thus opening up the first 40 rooms. But now an infinitely large bus with a countably infinite number of passengers pulls up to rent rooms. Countably infinite is the key. Now, the infinite bus of infinite passengers perplexes the night manager at first, but he realizes there's a way to place each new person. He asks the guest in room 1 to move to room 2. He then asks the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Each current guest moves from room number n to room number 2n, filling up only the infinite even-numbered rooms. By doing this, he has now emptied all of the infinitely many odd-numbered rooms, which are then taken by the people filing off the infinite bus. Everyone's happy and the hotel's business is booming more than ever. Well, actually, it is booming exactly the same amount as ever, banking an infinite number of dollars a night. Word spreads about this incredible hotel. People pour in from far and wide. One night, the unthinkable happens. The night manager looks outside and sees an infinite line of infinitely large buses, each with a countably infinite number of passengers. What can he do? If he cannot find rooms for them, the hotel will lose out on an infinite amount of money, and he will surely lose his job. Luckily, he remembers that around the year 300 BCE, Euclid proved that there is an infinite quantity of prime numbers. So to accomplish this seemingly impossible task of finding infinite beds for infinite buses of infinite weary travelers, the night manager assigns every current guest to the first prime number, 2, raised to the power of their current room number. So the current occupant of room number 7 goes to room number 2 to the 7th power, which is room 128. The night manager then takes the people on the first of the infinite buses and assigns them to the room number of the next prime, 3, raised to the power of their seat number on the bus. So the person in seat number 7 on the first bus goes to room number 3 to the 7th power, or room number 2187. This continues for all of the first bus. The passengers on the second bus are assigned powers of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers of 17, etc. Since each of these numbers only has 1 and the natural number powers of their prime number base as factors, there are no overlapping room numbers. All the bus's passengers fan out into rooms using unique room assignment schemes based on unique prime numbers. In this way, the night manager can accommodate every passenger on every bus, although there will be many rooms that go unfilled, like room 6, since 6 is not a power of any prime number. Luckily, his bosses weren't very good in math, so his job is safe. The night manager's strategies are only possible because while the infinite hotel is certainly a logistical nightmare, it only deals with the lowest level of infinity, namely the countable infinity of the natural numbers, 1, 2, 3, 4, and so on. Georg Cantor called this level of infinity Aleph 0. We use natural numbers for the room numbers as well as the seat numbers on the buses. If we were dealing with higher orders of infinity, such as that of the real numbers, these structured strategies would no longer be possible, as we have no way to systematically include every number. The real number infinite hotel has negative number rooms in the basement, fractional rooms, so the guy in room 1/2 always suspects he has less room than the guy in room 1, square root rooms like room radical 2, and room pi, where the guests expect free dessert. What self-respecting night manager would ever want to work there, even for an infinite salary? But over at Hilbert's Infinite Hotel, where there's never any vacancy and always room for more, the scenarios faced by the ever diligent and maybe too hospitable night manager serve to remind us of just how hard it is for our relatively finite minds to grasp a concept as large as infinity. Maybe you can help tackle these problems after a good night's sleep, but honestly, we might need you to change rooms at 2 a.m.
Okay, so that gives us a glimpse into the complexity of infinity. Particularly interesting, I found there was this idea that the room assignment at the end, where he has the infinite number of buses with infinite number of people, using the prime numbers and their powers would leave so many rooms empty, like 6 and I don't know, 10, 2 times 5, 10's not a power, all of those rooms. So it's really interesting to me to think about infinity and how we can try to wrap our minds around the notion of infinity. So hopefully, I hope you enjoyed that a little bit. So can you still see the slideshow? Yeah, there's a couple of videos out there similar. Yep. Yeah. Okay, great. So let's talk a little bit about cardinality, because that video was really getting at the cardinality of, so the number of rooms in the hotel is a metaphor for the cardinality of the counting numbers. So it does turn out that there are different sizes of infinity. We really, for any infinite set, we can't really say how large it is. Although there are, as was mentioned, orders of infinity, but you can't, there are larger levels of infinity, but we can't say specifically how large any one of those levels are because it's infinitely large. But we can say that one is larger, the same size, or smaller. That's possible with an infinite set. So there is one level of infinity that is larger than another level of infinity. And this relative size of the infinities is called the cardinality of the set. So cardinality and one-to-one correspondences, let's talk about that. So we can say that two infinite sets, A and B, have the same size or the same cardinality if there exists a one-to-one correspondence between them. So notice this means if we can find any function, and this is important, any function that takes set A to set B such that there is a one-to-one correspondence. Now remember, one-to-one is every member of the domain is mapped to a unique member of the codomain. So if we can find a function that takes every member of the domain and maps it to a unique member of the codomain, then we have the two sets have the same size or the same cardinality. So I'm going to make a claim here. There is the same number. Oh, let's see. Could one-to-one? Yeah. So Tanner, most lines do have a one-to-one correspondent. There are two types of lines that would not. Those would be the vertical lines and the horizontal lines. But assuming that we aren't talking about a vertical line or a horizontal line, all linear functions do have a one-to-one correspondence. There are some cubic functions that would as well. There's a variety of them, but I think the linear function is probably the easiest one to imagine for sure. Yep. Okay, so there are this is the claim. There are the same number of even integers as there are all integers. Now remember, if we want to say there's the same number, that means we're saying that the two sets have the same cardinality. And that means we have to be able to find a function that takes one set to the other set. So if I'm talking about even integers and all integers, so we could say, let A be the set of all integers and B be the set of even integers, then we would need to be able to find a function that would take the set of all integers to the set of even integers. So our set A would look something like that, where we'd have all of the integers, and set B would be something like that. Okay, so take a moment. I'll give you about 30 seconds. Look at those two sets of numbers. Can you create a function that would take the map the numbers in set A to the numbers in set B. So hold off, don't put anything in the chat yet. What we're after is a function that would take the inputs in set A and produce the outputs in set B. And I'll tell you when to do that in about 15 seconds. Okay, go ahead and drop in the chat. What could you do to map set A to set B? Okay, 2 times A. I'm seeing a lot of different ways to capture the same idea. That's awesome. Yeah, simply I could take each of the members of set A and multiply them by 2. So for example, h of 0 would be 0, h of 1 would be 2, h of -1 would be -2, and so forth. So I'll just click through this here. Oops, I clicked too far. So we could keep going, but keep in mind to show that A and B have the same cardinality, we need to show that there is this one-to-one correspondence. So we have a good idea here. We have a function, h, you use different notation, but I understood what you meant. So basically our function is we're going to take the number in set A and multiply it by 2. And so our function is h of n equals 2n. Okay, so first of all, we need to know that h is 1-to-1. That is, if for every x1 and x2 and x, if the outputs are the same or if the function values are the same, then our inputs are the same. So you saw this in the homework or in the lesson, sorry. So to show h is 1-to-1, we suppose that we have 2 outputs that are the same. And we're going to use the function definition to show that the inputs should be the same. So we're supposing h of n1 equals h of n2 for 2 numbers, n1 and n2 in set A. And what we want to show is that n1 actually equals n2. So since h of n1 equals h of n2, then we'll use the definition of h. Substituting n1 and n2 into h, we get 2n1 equals 2n2. And then we can divide both sides of the equation by 2. And we see that we get n1 equals n2, which was to be shown. So we know that h is a 1-to-1 function. And going back to, Tanner's comment, h of n, he asked about linear functions. Yeah, notice h of n, if I replaced n with x, you'd probably say, well, h of x equals 2x. Yeah, that's linear. So this is a linear function, and we should be able to show that it's both 1-to-1 and onto. We showed the 1-to-1 part. So let's take a look at the onto part. So h has to be onto, which means that for every y in the codomain, so every y in the every output, there is an x in the domain such that f of x equals y. So for every y in the codomain, there's an x that will get us to that y value. So what we have to do is just pick a random number out of our set B. And what we want to show is that there exists some number in our domain such that when we apply our function h to that number in our domain, that x, we end up with y. Now, this is where you saw us using a little bit of scratch paper to help us accomplish that. And the easy way to do that is to start with h of x and what it looks like. And so in this case, h of x equals 2x, and that's our y value. That's our y in our codomain. And what we want to know is, what is the x that's going to get me that y value? Well, I'm going to divide both sides of that 2x equals y equation by 2. And the x that will give me a specific y value is y divided by 2. So for example, if I chose 4 out of the codomain, the number that would have gotten me to 4 would be 4 divided by 2, or 2. So that's a quick example. So what we want to do then is to let x equal y over 2, using the information we got from our scratch paper. And we do want to make sure that we notice that x will be an integer, because remember, as we were doubling, because we doubled every integer, we ensured that all of the numbers in our codomain were even integers. So we want to notice that, yes, x is an integer, because remember, our domain had to be integers. Okay. So now we substitute that x that we chose, this x that is y over 2, we substitute this into our function h. So we have h is y over 2. Using the definition of h, it's 2 times whatever our input was. So 2 times y over 2, and we get our y, which was what we wanted to show. So we have h being on 2. So since h is 1-to-1 and on 2, we know that it's a 1-to-1 correspondence. And since there is a 1-to-1 correspondence between sets A and B, they have the same cardinality. So think for a minute. We started with all of the integers, and we doubled that to create our codomain. So what's missing, to create our codomain. What's missing out of the integers, though, in that process? You'll notice that there are no odd integers. Those are completely missing. So what we end up having is that the set of all integers, all of them, is the same size as the set of just the even integers. So think about that for a minute. If that's not mind-blowing. And this is because of the characteristics of infinite sets. It's really hard to wrap our minds around. So yeah, it just, every time I think about it, I'm like, no, it should be half as large, right? Because I'm missing half of the integers, but no. Based on the characteristics of countable sets, yeah. So a countable set, or a set, is countably infinite if and only if it has the same cardinality as the positive integers, z plus. So z plus, of course, is the integers 1 through keep going forever. And maybe a better word for countable might be listable, because the word countable might lead us to think, oh, I can actually sit here and count, and I can finish counting. Yeah, listable might be actually a better word. If we can make a list, even an infinite list of all the elements in a set, then we can say that that set is countable. So a set is countable if and only if it's finite. Well, that makes sense. Like that initial set I had that had the 4 elements, right? Countable, I could count them all. If it's finite or countably infinite. So that quick exercise we did with mapping the positive integers to the even numbers, okay? Countably infinite. So that is a countable set. We have a way that we can count them. Otherwise, a set is called uncountable. So if we can't devise a strategy, so this is it. It's really about devising a strategy for counting all of the members in a set. If we cannot devise a strategy to count all the members in a set and make sure we counted them all, then the set is referred to as uncountable. And uncountable sets, we're going to see, hopefully, I'm watching my time here. Uncountable sets can be a size of infinity even larger than the integers. Okay, so let's go as our claim is the set of all integers z is countable. So if I take positive integers, negative integers, 0, the whole shebang, that's countable. So at first glance, it seems like there are more than twice as many integers as the positive integers, right? So if I start at 1, 2, 3, 4, 5, keep counting forever, you know, that's countably infinite. And I'm missing from 0 to the left, all of those negative integers. And z plus is only that part, whereas the entire integers looks like that. So if we start counting or listing, if we think of it as listing, we could start at 1. We would have 1, 2, 3, 4, 5, and so forth. But as I said, we'll never get to the negative numbers, so that won't work. But we want a way to count or list all of the numbers in the set. We have to be able to have a strategy to do that. So what I want you to do is take a look at that number line. So we know that just starting here with 1, 2, 3, 4, 5 won't work because we'll never get over here to these negative integers. What I want you to do is take a minute and just look at the number line and think about, is there a way that you could think of that we could count all of the integers and not skip any of them, not skip over these negative integers? So what I want you to do is take about 30 seconds to think about that. And if you think you have something, when I give the go ahead, what I want you to do, so let me give you an example. So let's say this isn't the answer, right? So what I want you to do is order the integers to capture what you're thinking. So for example, I could put 1, 2, 3, 4, 5, but we know that won't work. So think about how you might order these, how you might list them so you could be sure to get every integer, and only put like the first 5 or 6 numbers in the chat. So I'm going to give you a minute to think about that, and then I'll let you know when to hit enter in the chat. Again, just looking for ideas on how to do this. Okay, so in the chat, start your list of integers showing how you would go about listing what you see on the screen such that you won't miss any integers. So go ahead and do that in the chat. Okay, got a few ideas there. Others? Okay. Okay. All right. Okay, so what the strategy you put in there is your listing, or is the one-to-one correspondence that you're proposing. So let's go ahead and take a look at what might actually work. So if Z is countable, if we can find any way to count or list all of the elements of Z exactly once, that way, this way of counting will be our function, our F, that is one-to-one and onto. So notice we may, just like the seats and the students in the auditorium, there wasn't like a mathematical function, but there was a way we could say that all of the students were in a seat and there were no seats that were unoccupied. This is going to be somewhat similar. There's not going to be like, well, okay, there might be a neat and tidy, but I wouldn't expect you to come up with it function that would do this mapping for you. So imagine starting at the middle. So 0 would be your first, then 1 and -1. I noticed somebody did -1. Oh, Robert. Yeah, Robert did -1 first. That would be perfectly legit. So start at 0, then do the positive and -1s, and then the positive and -2s, the positive and -3s. So we're creating an ordered list here in which each number, each integer has been assigned a position or is ordered in the list. So I could look at Robert's answer, and based on what he has there, I see that, at least for what he put into the chat, the cardinality of his set is 11. Okay. And that accounted for all of the integers that were on the screen. So, but if we keep going, and 6 and -6, 7 and -7, 8 and -8, eventually we will list all of the integers. So first of all, will we eventually list all of the integers using this method? In other words, will this method get everything in the codomain? Yes, because we're doing this very methodically and making sure that we're not skipping any. And will we count any integer more than once? No, we won't. So the set of all integers is countable because we created a strategy, we created a technique that ensured that no integer is counted twice. And so the function is one-to-one. And every integer got counted. The strategy didn't skip any integers. So the function is on 2. So the strategy defines a function from the positive integers to Z that is a one-to-one correspondence. Now, there is an actual function. If you want to know it, you can download the PowerPoint from Canvas. I would not expect you to to have that, to know that. So that's about countable sets. So, oh, good, we've got time for this. But remember, I mentioned there are these infinite sets that aren't countable. We don't have they are such that we can't create a strategy. They're so large. There's some characteristic of the set that makes counting or listing the elements of the set impossible. So we're going to watch another video titled "Infinity is Bigger Than You Think," and it's going to talk about these ideas far better than I could do it. So if someone could give me a thumbs up once
we're going to break a rule.
Oh, there we go.
We're breaking one of the rules of Numberphile. We're talking about something that isn't a number. We're going to talk about infinity. So infinity. Now, like I said, infinity is not a number, right? It's an idea. It's a concept. It's the idea of being endless, of going on forever. I think everyone's familiar with the idea of infinity. Even kids, you start counting 1, 2, 3, 4, 5. You know, you might be 5 years old, but already you're thinking, what's the biggest number I can think of? And you go, oh, it's 20. You get a bit old and you go, maybe it's 1,000,000. It never ends, does it? Because you can keep adding 1. So that's the idea of infinity. The numbers go on forever. But I'm going to tell you one of the more surprising facts about infinity. There are different kinds of infinity. Some infinities are bigger than others. Let's have a look. First type of infinity is called countable, and I don't like the name countable. And I'm really getting a little bit of a just then, because if you're talking about infinity, you can't count infinity, can you? Because it goes on forever. I think it's a terrible name. I prefer to call it listable. Can we list these numbers? All right, let's do the simple numbers. 1, 2, 3.
I'm not going to do all of my jokes.
4. How long have we got?
10 minutes.
All right, 5, 6. So you can list the whole number. So this is called countable. Listable, I prefer. What about the integers? All the integers, that's all the negative numbers as well. So there's 0, let's have that. But there's 1 and -1. There's 2 and -2. There's 3 and -3. Now that is an infinity as well. And in some sense, it's twice as big because there seems to be twice as many numbers. But it is infinity as well. They're both infinity, and they're both the same type of infinity. They both can be listed. Perhaps more surprisingly, the fractions can be listed as well. But you have to be a bit clever about this. Let's try and list the fractions. I'm going to write out a rectangle. 1 divided by 1. That's a fraction, that's about. Let's have 1 divided by 2, 1/3, 1/4, 7. Okay, that goes on. Let's do the next row and have 2 at the top. 2 over 1, 2 over 2, 2 over 3, 2 over 4. Let's do the next one. 3 over 1, 3 over 2, 4 over 6, 4 over 7. Now it goes on, and we can keep going. So here I've made some sort of infinite rectangle array of fractions. Now, if I want to make a list like this, though, if I went row by row, you're going to have a problem. If you go row by row, I'll go this. There's 1, 1/2, 1/3, 4, 5, 6, 7. I'll keep going forever. And I'm never going to reach the second row. I can't list them, not that way. You can't list them that way. You'll never reach the second row. This is how you list them. Slightly more clever than that. You take the diagonal lines. Now, I can guarantee that every fraction will appear on one of those diagonal lines, and you list them diagonal by diagonal. So that's the first diagonal. Then you list the second diagonal. There it is. Then you list the third diagonal. Then you take the fourth diagonal and the fifth. So eventually you are going to list every fraction. Every fraction appears on a diagonal, and you're going to list them. Now, if you take all the numbers, right? That's the whole number line. Let's try that. Look, I'm going to draw it. It's a continuous line of numbers. These are all your decimals. You've got 0 there in the middle. You'll go 1 and 2 and 3, but it has a third. It will contain pi, and and E and all the irrational numbers as well. Can you list them? How do you list them? 0 to start with, and then 1, but hang on, we've missed a half. So we put in a half. Hang on, we've missed a quarter. We'll put in a quarter. But we've missed 0.237. So how do you list the real numbers? It turns out you can't. And in fact, and rather remarkably, I can show you that we can't list them, even though we're talking about something so complicated as infinity.
Do it, man.
We need paper.
We need an infinite amount of paper here, I think.
It's a big topic. Imagine we could list all the decimals, right? We can't actually, but pretend we can. What would it look like? We'll start with all the 0 point decimals. Let's pick some decimals. 1, 2, 1. Let's pick the next one. Let's say the next one is 2, 2, 1. Next one. 3, 1, 1, 1, 1, 1, 2, 9. And let's take another one here. 0, 0, 1, 7, 6. Now I'm going to make a number. This is the number I'm going to make. I'm going to take the diagonals here. I'm going to take this number and this number and this number and this number and this number. Okay, and I am going to write that down. So what's that number I've made? It's 0.12101. Something, something, something. Now, this is my rule. I'm going to make a whole new number from that one. This is the number I'm going to make. If it has a 1, I'm going to change it to a 2. And if it has a 2 or anything else, I will change it to a 1. So let's try that. So I'm going to turn this into 0 point. So if it has a 1, I'm going to turn it into a 2. If it's anything else, I'm going to turn it into a 1. So that'll be a 1. I'm going to change the 1 here into a 2. I'm going to change that one into a 1. I'm going to change that one into a 2. That was my rule. And I make something new. That does not appear on the list. That number is completely different from everything else on the list because it's not the first number because it's different in the first place. It's not the second number because it's different in the second place. It's not the third number because it's different in the third place. It's not the fourth number because it's different in the fourth place. It's not the fifth number because it's different in the fifth place. You've made a number that's not on that list. And so you can't list all the decimals, in which case it is uncountable, it is unlistable. And that means it's a whole new type of infinity, a bigger type of infinity.
Surely we could, James, because all we've got to do is keep doing your game and making them and adding them to the list. If we keep doing that, won't we get there eventually?
But you could then create another number that won't be on that list. And so the guy came up with this, a German mathematician called Cantor. Cantor lived around about the turn of the 20th century. He was ridiculed for this. For this idea that there are different types of infinity, he was called a charlatan. And it was nonsense, it was called. And poor old Cantor was treated really badly by his contemporaries, and he spent a lot of his later life in and out of mental institutions where he died in the end. Near the end of his life, it was recognized. It was true, it was recognized, and he had all the recognition that he deserved.
And now he's on number 5.
And now he's on number 5, the greatest accolade of all. George Cantor.
So it's really interesting that he shared there at the end the story of George Cantor, because I mean, even today, as we think about, even tonight when we mapped the positive integers to the even integers and ended up with those two sets being the same size, it's so counterintuitive. It's difficult to imagine those sets being the same size. And then it's difficult to imagine a set that could even be larger than that. So he was an incredible mathematician who unfortunately wasn't recognized at the time for his contributions, although later in life, his contributions were recognized for what they were. So just to kind of close this out, this connection between sets and functions and infinity. So what we've seen is that the size of the set of the integers is the same as the size of the set of the positive integers, which is the same as the size of the set of the even integers. And as we saw in the number file, because there was a way we could list all of those fractions, even though he didn't go with the specifics, but there was a way to use diagonals to list them all, the rational numbers, all the fractions, those three sets are all of the same size. Because we can define a function, we have a way that we can list all those numbers. Whether we actually list them all is irrelevant. The fact that if we needed to, we could is what we're after. And that turns out that that's not equal to the size of the real numbers. The real numbers, all of those decimals he was talking about, there is no way to list them. If we try to list them as he showed you, you can always find another decimal that's not in your list. So in particular, the size of the integers is, or the cardinality of the integers is less than the cardinality of the real numbers. So those two sizes of infinity are very different. The integers, the positive integers, the even integers, even the rational numbers, those are countable sets. They're countable if infinity, often referred to as Aleph naught or Aleph zero. And the real numbers, they're uncountable. So they are a size of infinity much, much larger than the integers. So that's what I wanted to share with you tonight. All of those videos and the PowerPoint are available in Canvas. Do you have any questions? I hope you enjoyed that. Kind of something different.
Thank you.
Oh, sure.
So, like, was it not being recognized by his colleagues that drove him insane?
Yes.
Or was it infinity itself that drove him insane?
No, it was so he was ridiculed by the mathematicians of the day. They could not imagine that there was a set that you couldn't count. It blew their minds. And there's other instances in mathematics history where people, have been persecuted for their mathematical ideas that are actually found to be true. Okay, well, oh yes, thank you, Alexander. I hope you enjoyed that. This next week, module 10 is open. You're going to be looking at relations. This is, crazy. Like Aiden, I have no idea how he came up with that. I'm like, I got nothing. So module 10 is on relations. This is kind of building on the functions that we have been working with. And I want to encourage you to take advantage of the extra credit. For example, the extra credit in study groups. If you go put your name in the discussion, try and meet up with other students. It's a great way to finish your homework and get a little extra credit. And then I will stay around and answer any questions you might have. Other than that, I hope you have a great evening.
Thank you, Professor. You too.